So section 6.4, using systems to model data. So in the last unit, we learned how to find a line of best fit to a set of real-world data using linreg AX plus B. So this we found when we pushed stat and right arrow and button 4. In this unit, we learned how to solve a system of equation using 4 different methods. So first we started by graphing, where we looked at an intersection point. Okay, then the table method, where again we were looking for the common point they shared. The substitution method, where we solved for one variable in one equation and substituted in the other. And in the last section we looked at the elimination method, where we modified the equations to make sure that one of the variables, their coefficients were opposite, such that when we added the equations together, it eliminated one of the variables. So in this section, we're going to bring these concepts of finding linear equations to model real-world data and the concept of solving systems of equations together in one problem. So let's take a look at this first problem. So the winning times for a 500-meter skating event over the years are given below by gender. And we're going to let T be years since 1970. So T, we're going to basically take what's in the year column and subtract 1970. So this will be 3, 8, 11, 16, 23, 27, 31, and 36. Okay, so this is going to be our L1. Okay. And so it says to first identify the explanatory variable and the response variable. So the explanatory variable, the input variable, is the year since 1970, or the year. And so our T. Okay, and the output is going to be the winning time. So the winning time depends on which year that we're looking at. So winning time, our response variable, depends on the value of the explanatory variable. So in part B, we're asked to use the linear regression feature on the calculator to compute the linear correlation coefficient for the women's data. Okay, so this is from the last unit. So we would put L1, in L1 we would put these values of T, and in this case it said for the women's data, so in L2 we would put the women's winning times. So we would hit stat and arrow over to button 4, and then we would tell it to use L1, so we would actually have to type a second function 1 to type in L1, and then a comma, and then second function and 2 to type L2, and then we would hit enter. Okay. And on your screen, if we round that to 3 decimal places, it should be negative 0.988. And R is a unitless number, so there are no units that we put here. All right, so keep in mind that the value of R measures the strength and the direction of the linear relationship between the two variables. And R, so let's just write over here somewhere a reminder about R. R is between -1 and 1. Where -1 would be perfect negative relationship between the two variables, and a +1 would be a perfect positive linear relationship between the two variables. So this value we're getting really, really close to -1. So a really strong negative relationship between the year and the winning time for the women. Okay, so now if we look at the men's data, again using linear regression, so we're going to hit stat, right arrow, and 4 to choose linear regression. And now the input variable is still time, so second one for L1, but now we need the winning times for the men, which are in L3. So we're going to hit second function 3 for L3, and then hit enter. And so on the output screen, if we scroll down, we'll see that our value there is negative 0.997. Again, a really strong negative relationship between the winning times and the years. So as we're increasing the years, we're seeing those winning times drop. They're getting smaller. So now part C asks us if there's significant evidence of a linear relation. I mean, it looks close enough to -1, but is it really? Okay, so is there significant evidence of a linear relation between years since 1970 and winning times for women? So in the last unit, part of the cheat sheet for the exam included the critical value table. Okay, where in the first column we have to look up the sample size. And for this one we had 1, 2, 3, 4, 5, 6, 7, 8 data points. So in here we had 8 data points. Okay, there were 8 rows of data that we put in, 3 different columns, L1, L2, L3, but 8 rows. And we recorded information for 8 different people. Okay. So if we look up our number, we get 0.707. So what does that mean? Okay, R can be any number from -1 to 1. And this number, 0.707, tells us for 8 data points how far away from 0 we need to be close enough to -1 or close enough to 1. Okay, so in here this is going to be significant evidence of a positive linear relation. And if R is in here somewhere, just remember this is an R axis, and if R is in here, this is going to be significant evidence of a negative linear relation. Okay. Well, the R value that we got for the women was -0.988, okay, which is in here. Okay, so we do have significant evidence of a negative linear relation. Okay, so is there? The answer here is okay, yes. Okay, our -0.988 is between -1 and -0.707. So then we're asked if there's significant evidence of a linear relation between the years since 1970 and the winning times for the men. Okay, well, for the men we also had, there were 8, just like up here. Instead of calling them data points, there were 8 women, okay, in the study. And here there were also 8 men in the study, so our sample size is 8. And so again, we have the same value of R, critical value for R. So again, R is always a number between -1 and 1. And again, this gives us how far away from 0 that number needs to be considered close enough to 1 for a positive relation or close enough to -1 for a negative relation. And again, our value we got for the male data also falls in this interval between -1 and -0.707. So there is significant evidence. Now let's say this had come out like -0.697. Okay, that would have been in here. And so then there would not be evidence of a linear relation. So all of these values in here, not evidence of a linear relation. Okay. But if it gets over 7.07, it's strong enough evidence of a positive linear relation. And if it gets below below -0.707, then there's evidence of a negative linear relation. Alright, so now it says to use the linear regression feature to find the function that describes the relationship between the years since 1970 and the winning time for each gender. So these values were actually on the same output screen where we just got R. Okay, so for this one, and we're going to put a little hat on top here actually, so the estimated winning time for the women was -0.1713 times T plus 43.5355. Now on your screen it says y equals ax plus b. But again, we're going to put the input variable here is really t for our equation. So we're going to replace x with a t. And then our estimated winning times for the males, given this year since 1970. Again, on the linear regression output screen for the male data, we got 1446 t plus 39.5 0.8476. So again, thinking about as we graph these, this would be our slope, and this number would give us our y-intercept. Okay. So we can see the slopes are different, so we know these two lines will need to intersect eventually somewhere. We do see that they have negative slopes, which makes sense because we got negative values of r as well.